10 million lashes, but I no cry. 10 years burial, but I no die. Take what's rightfully mine. Take what's rightfully mine. But that aside, you don't know me, you for Google. I say this head bigger than your dugu. Stubborn academy, we like to shoot too. One bullet, I say chale, it go make you poo poo. On a bicycle, so take your trailer and I'll be fair.
Alright, so today we are going to be looking at the capacitors, and we are going to see an overview of what a capacitor is and what it looks like, and we are also going to solve a question concerning the capacitor. So let's go. We have the capacitor. Now a capacitor is made up of two conductors. Okay, and these conductors are separated in a distance which we call d. So each conductor is having their charges. So and the charges between the two conductors are opposite charges. So the first conductor has its own charge and the second conductor has an opposite charge. But the charges are equal. So the charges are equal, but they are opposite. So the same number of charges we have here, but opposite charges. So now, most capacitors, you can see that the distance separating them can be an air separating the distance. Sometimes a liquid can be placed in the capacitor, which we call the dielectric. So now we look that in each conductors, the charge in each conductor is proportional to the potential difference that is created in the capacitor. So which we have that the charge is directly proportional to the potential difference, and the charge will be equal to, if I remove the proportionality sign and introduce a constant, let me call it C, then it will multiply with with V. So we have a constant here. So each capacitor has its own constant. So this constant is called the capacitance of the capacitor. So that's the constant. So the capacitance of the capacitor is C, and this capacitance of the capacitor is measured in farads. We measure it in farads. So we measure it in farads, which we can use just F to show farad. So if I give you 2 farads, I'm talking about the capacitance of the capacitor. And we have seen from our last class that the Gauss's law tried to give us a relationship between the electric flux and the net charge with the permittivity of free space. So we have in that formula that the flux is equal to the net charge all over the permittivity of free space. So now this flux, you can also see that from the last class we also said that the flux is equal to the electric field times the area. So in that case, I have 2 equations here, equation 1 and equation 2. So if I should go to equate the 2 equations, because they are both related to the electric flux, this is also related to the electric flux. So you can see that we have EA will be equal to the net charge all over the permittivity of free space. So which we can make E the subject formula. What we'll be having is E equal to the net charge, then the area times the permittivity of free space. And we can remember from our current electricity that the electric field is related to the potential difference. So we write that the electric field is equal to the potential difference divided by the distance. So the distance here is D, and the potential difference is V. So when we divide the potential difference and the distance, what we are going to calculate is the electric field. So this electric field intensity is the same as what we have here. So we can equate this equation, so V over D, into this. So that implies, instead of writing E, we'll be having V over D, which is now equal to Q all over A E what? A naught. So we can make V the subject formula. So since in this question we are looking for the area, let's make A the subject formula. So if I should cross multiply, and make A the subject formula, so we are going to have that A is equal to QD all over V E naught. So that is our area. So we can use this to calculate this. But you can also see that we have said that Q is equal to CV. So in place of Q, I can put my CV. So that means that A is the same as Q, which is now CV, then D all over what? V E naught. So clearly V, we cancel out V. Then we have that A is equal to CD all over epsilon naught. So we can calculate the area. So the question here is, let us calculate the area when we consider a capacitor with a capacitance of 2 farads and the distance of separation between the plates or the conductors is 4.5 millimeter in an air gap. So we use this formula to do the calculation. So we have, from the question, we are given the capacitance of the capacitor, which is 2.0 farads, and we are also given the distance, which is 4.5 millimeters. And what we also need is the permittivity of free space. Now, the permittivity of free space, epsilon naught, is a constant, which is given as 8.85 times 10 raised to the power minus 12. So, which is in farad per meter. Now, if we substitute, we have a problem with the distance. The distance is in millimeter. So we are going to convert it from millimeter to meters. How do you convert from millimeter to meters? You divide by 1000, or you can simply say times 10 raised to the power minus 3 is now in what? In meters. So in that case, our area will be equal to C, which is 2 times D, which is now 4.5 times 10 raised to the power minus 3, then divide by the permittivity of free space, which is 8.85 times 10 raised to the power minus 12. So if you should punch this in your calculator, you'll be having 1 times 10 raised to the power 9 meter watt square. So that gives us the area. So with this, we are able to calculate the area of the plates in the capacitor. So in the next class, we are going to look at some calculations that have to do with the capacitor, but this time the space is not surrounded by air, rather it is surrounded by a substance. So which we are going to look at and see how we solve such question in finding the area or the capacitance of the capacitor. So see you in the next video.